Hello, I am Dr. Sandeep Waghuley from Department of Physics, Sant Gadgi Baba Amravati University, Amravati. In this lecture, we will see about the atomic structures in nanocrystals. This is our department on globe. This is our laboratories. The man behind the nanotechnology is a very famous and eminent personality. That is Richard Feynman. He got a Nobel Prize in 1959. These are the definitions of nanotechnology, and are very simple definitions, but this lectures is for the MSc final year students of physics of all Indian universities. So we skip this and directly we will come to the point of nanostructures. Now in nanomaterials, actually we have to see that the atomic structure, what types of the atomic structures are there. These are the crystallography actually, and now in crystallography, that is we have to say that the solid state of matter can be put into the two broad categories on the basis of their structures. That is a crystalline or non-crystalline. Non-crystalline, which is called amorphous nature, means it is not in a crystalline state. If we got the X-ray diffraction pattern of that amorphous material, that shows the very nicely plot, whereas the crystalline has a very sharp peaks. But in nano materials, this shows the broader FWHM. That is the full width half maximum. Now the crystal lattice. Actually, the crystalline materials and crystal lattice is from the definition from of crystal lattice, that is atomic arrangement at one location looks exactly the seminal respect as a arrangement at corresponding to the location somewhere else. Means in this crystal lattice, these are the lattices, and that shows the unit cell, means the position of the unit cell in the atom. For this, we consider the parallelogram or the rectangles based on the translation vectors, and these are defined as the unit cells of the crystal. To understand the importance of the unit cell, let us consider only one of them, and it is apparent that under the action of the translation operation, we have to see that the crystals and the lattice arises from the continual replication of that unit cell throughout the space. In this way, the lattice plus basis that forms the unit cell, lattice plus basis, that is a crystal structure. We have to obtain the crystal structure, so that the distinction between a lattice and crystal structure becomes very easy. When we go through the space groups, that is in two-dimensional, they are very easy. Space groups in two-dimensional, that is a 17 possible arrangements we have to obtain here, and in two-dimensional, the lattices are oblique, rectangular, primitive, rectangular centered, then square, hexagonal. These are shown in this table. There is a four four group systems are there, and conventional unit cell, that is a oblique, is corresponding to the conventional unit cell is a parallelogram actually, and rectangular is a rectangle. Then hexagonal is for the 60-degree rhombus. In this way, in case of two-dimensional, that is a two-dimensional space groups are that are possible for a crystal with a square lattice to have only the operations 4, and in case of 3D, that the situation becomes is more complicated in case of, because there are the 230 space groups divided among the systems in the, that is the systems is in case of we have to see that from the triclinic to the cubic means triclinic, then cubic is monocubic. Actually, orthorhombic means all these are the 233 dimensional space groups we have to obtain here, and three dimension pictures becomes complicated due to the additional symmetry. That is, it becomes complicated due to additional symmetry elements and due to the added dimensionality itself. That's why it becomes now in certain special cases of crystal structures are important for the nanocrystals, such as face-centered cubic, then body-centered cubic, then face-centered cubic. Means in this way, SC, FC, BCC, and FCC means these are the very famous and basic types of the crystal structures. We have to see here that now these hexagonal pack structures, among these we have to say that the structural arrangement, that is a stacking planar hexagonal layer, and for a monoatomic crystal that provides the highest density or a close pack arrangement of identical spheres. In case of the hexagonal pack, that is close pack structure consists of the close pack layers of atoms placed one above the other, with the atoms of each layer sitting in the depression of the lower layer. In this way, AB hexagonal pack structures we have to obtain, and another face-centered structures. In face-centered structures, that is a structure which is formed when the third layer is added to the stacking sequence AB in such a way that its atoms are in position corresponding to C. That is ABC, and this arrangement commonly found in nanocrystals. In this way, body-centered cubic is there also, that is a BCC structure, and these BCC structures have contains only one atom associated with it. Considerations similar to those dictated with the reference to this FCC structure, and make it clear that the BCC unit cell is usually conventional over the rhombohedral primitive cell. In case of the nanostructure materials, that is that materials having a properties that depend on the crystal structure, but another properties such as the catalytic reactivity and absorption energies that are applicable in case of the photovoltaic cell applications. Some sensor applications are there, that because they are exposed to the surface. Now another case of the thin film technology, actually epiaxial films prepared from this FCC and FCC crystal generally grow with the planar close pack, means that shows these structures, and FCC crystal that expose surfaces with the same hexagonal 2D atomic array. In this way, in this lecture, we will see about that the that is a crystal structure, that is atomic structures in this lecture, and in the next lecture we will see about crystallography, how to determine the the crystal structure by using some techniques. That is there are the many techniques are there, that is the X-ray diffraction, then transmission electron, scanning electron microscopy. Then we will see. Then thank you very much.